Welcome back, everybody. We are right in the middle of this example last time. So we're going to continue with this. I'll remind us about the 75% coverage set. But I want to just remind us that a confidence set per interval, or whatever it is. So it could be a point, that's a set. So confidence set, interval, these are coverage sets. So these are statements about the process, really. So we kind of studied that to some degree. So here's the example from this example for this process right here. So this is a statement about a process. I'm going to describe what happens when I get two data points from this process. I could see one of two things. So I could either see x1 is equal to x2, or I could see x1 being different than x2. So x1 is equal to x2, or x1 is different from x2. And I'm going to report back some estimates in some sense of what I believe theta is in these various cases. So I'll give us some notation here. This is the confidence set. This is going to be, I'm going to give you x1 minus 1. I'm just going to make an arbitrary choice. I could have also given you x1 plus 1. And so I just decided I'm just going to give you this. That is some estimate of what I think theta is. And in this case, where they're different, I'm going to give you the average. So just as a reminder, let's say this one was theta plus 1. Then this one is theta minus 1 because of the constraints on the problem. There's only two possible contending values of this. And so when I add those two things together, I get 2 theta back. And this thing is always equal to theta. How often does that happen? That happens 50% of the time. This is the other 50% of the time. Right here, how often does that one hit theta? When this value right here was this, right here. So if I subtract 1 off of it, it gives you theta back. So this gives you theta 100% of the time, which happens 50% of the time that it happens. So conditional on this event happening, this is guaranteed to give you theta. This thing, this conditional statement, only happens 50% of the time. So the joint probability of this event is 50%. So this gives you back theta 50% of the time, i.e. it's that one and not that one. And this happens 50% of the time. So this gives you back theta when I end up looking at the joint of both of those events 25% of the time. So this happens, this gives you theta 50% of the time, this happens 50% of the time, 50 times 50 is 25. So this is a 75% confidence set. So it's a statement about the process of how often will this cover theta and give you theta back. So, and I kind of argued this is kind of a bad answer to give somebody. And so the name of the game is that you always report back the confidence level. So you're always saying 75%. And on average, you're right. But for any individual answer conditional on the 2 data points, we kind of could say more. I should probably say I'm 100% sure about this, and I'm only 50% sure about that. But that's not what's baked into confidence intervals or confidence sets. It's a statement about covering in the long run average. So, and that's what it's all about. So this example is designed to show why that interpretation might be misleading in some cases. We looked at another example where we were trying to infer mu from a normal distribution, and we came up with x bar plus or minus 1.96 times the standard error. And the frequentist knows that that covers true mu at a rate of 95%. So 95% of the time, that interval will cover as I collect data more and more and more. So this is probably what they should have dwelled on in undergrad class when they were first teaching this. But all they said is, just don't think it means that the parameter's in the interval. I don't know, I'm kind of extrapolating from my classes that I took. So that's what I heard all the time, and I was always like, okay, I guess the name of my game in my process is to get an A. So, okay, moving on. People apparently fight about this stuff. So, but now at least you have an example that shows kind of the deficiency in that sort of an answer. For the normal example, the Bayesian also gives you x bar plus or minus 1.96 standard errors. So, and they interpret that as the probability of mu being inside of the interval. So, and they call that a credible interval. So the Bayesian interval is this one. This is what I would call the frequentist interval, but it's a statement about collecting more and more data. It's not a conditional interval. It's not conditioning on your actual data set. And for the Bayesian, they also come up with the same interval in the normal example, but they think this is a belief statement about the parameter. Back in my day, people would fight about this, what the correct interpretation is. I don't think there's a correct interpretation. It just depends on what you're doing with the whole thing. And I think in the normal example, everything is really beautiful, where everybody gives the same interval. Some people say it's where mu lives under the flat prior, and some people call it the coverage interval. And it turns out it's both. So I don't see that being a problem. This is an example where the Bayesian and the non-Bayesian might not completely agree. Nobody is contesting that that's a 75% confidence set. You just have to understand what this word confidence means. So usually when people tell me you should be confident, I get a little bit nervous. So I'm not sure where this terminology came from. So credibility. Anyways, they needed another word. So here's the Bayesian interval. So the credible set. So what the Bayesian is always going to do is they're going to build a posterior first. So that's what all Bayesians have in common. So I'd say all the branches of Bayes, all the different ways of constructing priors and what they're actually giving you and what the interpretation of the prior is, that might be different between different types of Bayesians. But all Bayesians are going to do inference off of a posterior distribution. And so, and if you know what the process is, there's no arguing over what the likelihood function is. It's baked into the sampling process. It's just re-envisioning the sampling process, but making it a function of the parameter. So the parameter in all of this is just theta. And as we've already talked about, that's a location parameter. So that's just shifting these two bits around, however you want to think about them. Heads, tails, 1s, 0s, but there's some other number. So theta plus 1, theta minus 1. So credible set is first build the posterior. So step one, I always think it's the likelihood first. Now, I could totally rationalize somebody that, thought, well, I should have my prior beliefs. And that gets into this very sort of subjective land, that you know something about theta and you're willing to say it. And my experience is that's a bit of a turnoff for people. That it's like, well, what if I didn't? And I think in a lot of cases, you don't. But in some cases, you do. So it's okay to think that way. If you knew a lot about the problem you're studying, but I always am likelihood function forward. And the likelihood function we can all agree on. Like, it has utilities in frequentist land. I will point out it's the thing that shows up in the Neyman Pearson lemma. So there's different ways of utilizing likelihoods. So Bayesians utilize it by constructing a posterior. So the likelihood function for these two data points the functions of the 2 data points, and they're actually being conditioned on those 2 data points. And so my belief statement is not a statement about the process per se. It has the process built into everything, but it's not a statement about going and getting more and more data and seeing what happens in the long run. So it's a statement about what I believe after I see those 2 data points. So I will point out credible intervals or conditional intervals. And I really like conditioning. Where does conditioning come from in the Bayesian construction? Through the likelihood function. So what does this look like? This is going to be proportional to this product over 2 data points, fxi given theta. Let me make this PR or something like that, because these are actually probabilities. So the thing that I'm the most inconsistent about throughout all my classes, what do I ever call this function? Usually I just write down f. Why f? I don't know. So it probably should be P or PR. Anyway, this is this right here. I goes from 1 to 2. This is going to be 1/2. And I'll just write this down. This is going to be delta xi is equal to theta plus 1 times 1/2. Delta function xi is equal to theta minus 1. So they're just indicators of which event happened, turning on either this 1/2 probability or this 1/2 probability. We could even forget about that part. So a lot of people stop right here and they just recognize the probability is 1/2 of these things, and they're used to thinking that way. But if I ended up just writing out this bit right here, this is just 1/2 under all cases. So there's something more being multiplied in right here. So we haven't fully articulated the process in this function, and the function has to articulate the entire process. So let me just rewrite this over here. I goes from 1 to 2. Rewrite it again, 1/2 delta function xi minus 1, 1/2 delta function, so just a 1 or a 0, an indicator variable, xi plus 1/2. This was the part that we kind of guessed at. It's just the product of these 2 things. This is the fundamental mistake you can make in this class. So it's when you write down a likelihood function and it doesn't have the parameter involved. So I'm happy to say, this is theta is equal to xi minus 1, and this is theta is equal to xi plus 1. Very typically, you put the argument in there and you put the parameter down there. So I'll just stick to the same convention. So this part right here is always 1/2. So the product over those 2 things is 1/4. And if you write down a likelihood function like that, and you notice that it's flat and it doesn't have any information about the parameter, you've probably written down the likelihood function incorrectly. So this would mean the data has no information in some sense about the parameters. There's a problem there. So we haven't constrained the problem quite right. I need to also indicate the values that xi's can take on. So xi is either equal to theta plus 1 or theta minus 1. So I have to bound the problem and constrain it the way the data comes to me. So I need to articulate, there's only 2 possibilities for those values. If you stick any other xi's in there, other than these 2 values, theta plus 1 or theta minus 1, it'll be 0. So it can only take on these 2 values. Now, of course, I'm thinking about that from the perspective of the sampling function right here when I say it that way. So I write down the likelihood by writing down the joint distribution. And then I change my mindset and I start thinking about this as a function over theta. So turns out this proportionality part gets rid of all this stuff right here. So this actually has nothing to do with the likelihood. It's a statement about these probabilities. Now if I changed those numbers and said this was P and 1 minus P right here, that's what would be going up here. And that would have information about the p's, but I've told you what the p's are. And we're just focusing on the shift parameter.
Could you also write it as just a sum of two delta functions, one centered at theta plus one centered at theta minus?
If I sum two delta functions, what could happen?
If they go on top of each other.
If they go on top of each other, I don't care which way I sum. They taught me after third grade I could sum not in that direction, but I could also go in that direction. Maybe product. Let's look at it in a second. If I sum two delta functions, I could get 2. 1 plus 1.
Oh.
So that's probably not the right operator. Multiply. See it in a second. It's right here. So I just need to write it just a little bit differently. So let me rewrite this. The likelihood. So high. Instead of figuring out how to lower the chair for 2 minutes. Stay here. Likelihood function. To rewrite it proportional to the product of these two delta functions. I goes from 1 to 2. Xi is an element of these two things. Or I could rewrite it like this. I'll do it in the same order. The minuses switch to pluses, the pluses switch to minuses. So all I'm doing on this step right here is if I had theta is equal to x1 plus 1, I'm rewriting that as x1 is equal to theta minus 1. So I'm doing that for both of them. And I'm just pulling that around. So what am I effectively doing? I'm effectively pivoting. But really, I'm just rethinking about, in a non-technical sense, what does it mean theta is? If I know what the xi's are and I know this connection through the model, then I know what the thetas are, or at least what the contending values are. So now I'm thinking about it in terms of theta. And so the other part doesn't help me. It would only help me if I didn't know what those probabilities were. So now I can just rewrite this thing as the product over these two values. So theta is an element of x1 minus 1, x1 plus 1, times theta, delta, theta is an element of x2 minus 1, x2 plus 1. I see what you're saying right here. I think this is what you're pointing out, is I can think of this as a union.
Yes.
And that's where the add in your mind is coming from. It's that one or the other one. And so it's either a 1 being added to a 0 or a 0 being added to a 1. You could rewrite it that way. I'm going to keep it written joint and just check it. So let's just see what this function looks like. Yeah, I could probably rewrite these as a sum, but I would have to reconstrain them. That might be more difficult for me to write out. I like it like this. Let's just look at what this is. Let's just imagine this process. Let's give this some numbers so we can think about this. So let's imagine theta was 3. So here's just an example. Theta is equal to 3. And there's basically two cases. It's not basically two cases. There are two cases of what could happen. So case 1, x1 is equal to x2. I guess I could break this case up into a bunch of different, I could break this case into two cases, but I'm going to leave it general like this. And I'm just going to imagine what we end up seeing here. Let's imagine that this right here was a 4. So that's a 4. So if theta is a 3, this could be a 4 or a 2. Those are the only possible values. So this is a 4 for the whole thing, or a 2 for that whole thing. So let's say I saw 4s, and just look at this indicator function right here. So the likelihood, L theta, given our 2 data points. This is a function over theta space. Theta can be any real number. So this lives between negative infinity and infinity. Despite the discrete nature of the problem, there's a very continuous aspect to this problem. And so let's say I see 4 and a 4, so this is going to be a 3 right here, and that's a 5. This is right here, 3, and that's a 5. Right there, same exact thing. So this means that when this takes on either a 3 or a 5 right here, that's a 1, or a 0 otherwise, and this does exactly the same thing. So this reduces to just one indicator. Square that indicator, it's still the same indicator. So this is going to peak at 2 different points. So 3 and a 5 and 0 everywhere else. So this likelihood function, you can make any height. It all means the same thing. I can multiply by the quarters. I can multiply by any number. It doesn't really matter to us. So the point is whatever I multiply against, is these have the same heights as each other. So they're the same thing. Same weight on both of them coming through the likelihood function. So case 2. And you can probably see why we went with just 2 data points instead of a whole bunch. You could extend this example into something much more complicated. But case 2, x1 is not equal to x2. So that means I saw 4 and I saw 2. It doesn't matter the way I put these in. This is exchangeable. It doesn't matter what the order was here. Just like any binomial problem. So 4 to 2, let's just look at these. So x1 is a 4 minus 1, that's a 3. This is a 5. So and then x2 is a 2. So x2 minus 1, that's a 1. x2 plus 1, that's a 3. And that's all the magic right there. So this happens automatically through the likelihood functions. My favorite part of likelihood functions is they condition on things correctly if you've written it down correctly. So when this is a 5 right here, this is a 1. But when it's 5 over here, this is a 0. So they product together, that's a 0. It can't be 5. So when that's a 1, this is a 1, but that's a 0 right there, so it can't be 1. So we can exclude out those possibilities. When it's a 3, that's a 1, that's a 1, and that's the only point in the entire space where this has any weight. This is 3, and that's theta. That's what we already know. So this peaks at 1 point. So, and this would be our answer. It doesn't matter how high you make this again. Just a likelihood function. The point is this is the only place this has any mass in the entire continuum. Now let's just think about our priors. So the second part to doing a Bayesian analysis is our prior. From our last lecture, we were pretty quick to say it's a location parameter, let's use flat prior. So let's go with that. Let's think about this case right here. My flat prior across this thing, whatever height I put this at. This is just arbitrary. I'll write it in as 1 just because it's convenient to do so. Then I normalize everything. Well, it only takes on value at 1 point anyway. So the posterior distribution is just this 1 point. This doesn't have any width. Right here, it has 0 width. It's just a point mass. So it's a 1 at that one point and 0 everywhere else. And that adds up to 1. If you integrate over this, if you would like to, it's just an indicator at one point. It's normalized, so it's normalized to be 1. So this probability would be 1. So this has posterior prob equal to 1, and that's for this case. And it doesn't matter how I picked theta. I could have picked theta differently. I could have picked it uniformly in any which way, and I would always have this property. So I've got uniform performance over the whole range of theta. So that's what we mean when we say it's like uniformly performing. Same performance over all of theta. That happens here too. So in this case, regardless of how I picked theta, I just picked it for some numbers. We could have picked it arbitrarily. I would get the exact same performance out of it. And the point is that once we normalize everything, if we use the flat prior, this is my prior, I'll just arbitrarily draw it to have height 1. These have the same height. They've been normalized. So they both have probability 1/2 on each one of those points. So each has posterior probability. And that is an artifact of the prior I chose. So if I had picked a different prior, I could have done something different. What it would do is it would weight this one higher and that one lower. So let's say subjectively you knew Scotland loves playing this game, but he always picks smaller values of theta than we're inclined to believe. Now, you might construct a prior like that. You would have to know a lot about how I pick my thetas. So it's true. I usually pick numbers like 3 and stuff like that. I usually don't pick like 3 billion. So just because, I don't know. They're the numbers I think about the most often, maybe. Something like that. I don't usually pick numbers like 3.1121, something irrational and never repeating. So anyway, you could encode that, but you get my point. If you knew something about those numbers, you could construct your prior differently. But you wouldn't be learning about that through the data. The likelihood function would pick up on all that. So I would probably say there's no good reason with the problem as stated to pick anything but the flat prior. So, but it gives you room, or at least a knob or a lever, if you did know something to encode it. I think that's probably what people got most worried about back in the 50s and 60s as Bayes is starting to be talked about. What's this prior thing? Does that mean you can make anything up? I wish they just said no. Probably not. I mean, you could, but nobody's ever going to believe your analysis. So, but I think from a pure philosophy standpoint, it's fun to think about things that way. And that's probably what they were arguing early on. It probably wasn't until the 90s came around that people said, oh, this is pretty useful stuff. And that's all about MCMC that we're going to go to next. So that'll be our next set of lectures. So I want to just point out the Bayesian answer right here, if I gave just this point, right here I said I'm just going to throw one of them away, and I just pick one arbitrarily. And in this case, I always give the right point. You have a 75% set as well. I would articulate it differently. The answer I would want to give is not this 75% confidence set where you always say 75. I would like to make these conditional statements where I'm conditioning on all the information in the data and I'm not making a probabilistic statement about the process. That when I saw this case, I'd like to say probability 1 and not 75. But I could use this to construct a 75% coverage. I just don't see any good reason to do that because I don't think that's a great answer. So I will point out that this Bayesian answer has the same 75% set if I used it that way and I only gave back one of those answers, but instead of just giving back one of these answers, I'd like to say, I think the answer is either 3 or 5, and each have probability 0.5. Turn that into any set you want. You know, what set would I turn it into? Those 2 points, and I would say this right here, these 2 points, creates a 100% confidence set. So the Bayesian can be a frequentist, depending on how we want to articulate ourselves. So I could say this is a 100% confidence set, answers in there. This is a 100% confidence set. What's different is I'm conditioning on the 2 data points. So it's a conditional confidence set. And if you've looked at that paper on Jeffries, Fisher, and Naiman, the answer to the question, could they ever have agreed, is no, not on anything ever. So Fisher wouldn't have agreed with anybody. Definitely not Naiman, and definitely not Jeffries. So
is the argument for using the credibility interval here is that fixing the confidence leads to sort of a bad summary?
yeah, because you're averaging over data sets you never saw. So, and that's the basic argument we'll make when we get to p-values later on. So when we do hypothesis testing, I'll say you're averaging over stuff you never saw. And that's baked into the answer. And is that meaningful? So I will point out in hypothesis testing, Bayesians have deficiencies too, and I'll try to be thorough about what they are. So I'll be at least as thorough as I can be in a week's time. But yeah, I think so. It's not a statement about averaging over all this stuff you haven't seen. It's conditional on just the data. I like that answer. If you wanted to be ridiculous, you could just give back one of these answers and say, I'm 50% sure. What's the other one? I don't feel like telling you. So I really like this. The real summary of this, I think the answer is this picture. So that's it. Or you could table it, anything like that. But this is just distinguishing characteristics of confidence sets and credible sets. So I will point out this. There's no obligation for a Bayesian to cover. So they may or may not. This example is one such example where they're perfect frequentists. And probably could give you really good frequentist summaries of everything and construct a 100% confidence set. Another 100% confidence set, I could construct that as well, is saying it's the whole real number line. And in both cases, no matter what, I'm going to give you it's between minus infinity and infinity. And that's 100% as well. But this set has a different property. It's the shortest such set that has 100% coverage. So I just want to be clear, Bayesians don't always cover. But you might want to know if you have frequentist friends and they say, I learned this thing in Stat 101, how does your thing compare? What would you do as a Bayesian and you weren't able to draw it out so clearly, you're working in a high dimensional space and you didn't know, you could always simulate and build a simulation study and say, oh, the prior I chose has this property that it's like 94.2% coverage, which is actually probably pretty good. Usually in complicated problems, when people say I'm doing the 95% thing, I bet they're not even close. And if they say, well, we're actually higher, we're like 100. I did a simulation study. That makes me really worried. So, because then I'm thinking, did you make your sets way too big? So frequentists also have the paradigm of trying to come up with shortest intervals. We usually don't talk about that because it can be exceedingly hard to do. So anyway, there's different properties that the 2 different branches might have. The point is in some cases you could have both. And you probably won't know you have them both until you do simulation studies. So I encourage you to do that. Because just saying theta's in here, that's what I believe, isn't enough for me. Because I might be worried you came up with some ridiculous prior. How did you pick your prior? Why did that make sense to you? I want to hear about your whole construction about everything. So belief isn't enough on its own as well. So, but I think putting these 2 things together is a nice compromise. So I believe in that compromise of being a frequentist when you can, but I usually do it through a Bayesian lens. So if there's one thing you can learn from this class, besides making sure your likelihood functions aren't flat. So it's that you can be both a frequentist and a Bayesian simultaneously. And sometimes the conditional frequentist answer that a Bayesian will give you is superior than just some blind coverage set, the 75% set being the example of. That's just a bad answer, and reporting back 75% in these two different cases doesn't seem smart either. I also want to just point out, just as one last caveat, I don't think any of my frequentist friends that I've ever met ever would have said the 75% confidence set is a good answer. So I'm pretty sure they would have constructed this and had some other lens to look through and said, well, I've constructed it. Question is how do you come up with a conditional confidence set that's right? And nobody has a paradigm for doing that. In this case, the Bayesian gets it just for free, and it all came through the likelihood. So likelihoods can be powerful frequentist weapons, even in Bayesian cases. Let me just show you, this is more of just a glossary definition, the highest posterior density. So I'm talking about densities here. So I'm thinking about continuums when I talk about this. But this same analog extends to this discrete set. So highest posterior set would be this one. So it means that it's the shortest length set. This is just 2 points. I understand that length can't be quantified quite right. So we're not in real math class. So, but this is in some sense is the shortest set. I get it. If I put another point right in there, it's got the exact same length compared to the continuum. I'm not talking about anything confusing like that. So this is the shortest set, which means it has the highest density. So densities always add to the same number. So if we just think about what the word density means, it has to do with the mass of something and the volume of something. So that's the way we usually think about it three-dimensionally. So why does a boat float? You know, this sort of thing. While it has a great amount of mass, it also has a great amount of volume, and it's not very dense compared to the water, so it floats. So the mass is fixed in a posterior analysis to add up to 1, so the only thing we get to play around with is the volume. In a one-dimensional case, we might think of that as length. So it's the smallest set, or the shortest set. You can extend that same concept to high-dimensional spaces, and you just talk about hypervolumes. So HPDs, you'll hear people discuss, and all they're asking for is your shortest Bayesian interval. So let me just draw you an illustration. Oh, let me make this more dramatic. Okay, let me draw not a HPD real quickly. So we will cover this. This is going to be an equal tail. This is not an HPD. I'll show you an HPD in just a second. So I'm going to let this be a 95% credible interval. So what I'm going to do is I'm going to chop off 2.5% right here. So 0.025. This has been normalized. It all adds up to 1. And this right here is 0.025. That's the areas in these tables. So that's one such interval. So I would report back this thing. Boom, boom. So this is left, this is right. So that's a pretty lazy answer. So the Bayesian could go back and say, No, I'm 95% sure. It's my belief that the parameter lives here. And I think they're saying something correct. But when you look at the picture, it's kind of peculiar, especially if I brought this all the way down. Let's just do that. All the way down to 0 for like some little stretch in here. Why am I including that? And so to do that, I had to include a lot of this area and dig deep into that thing. And what I've done is I've pushed this farther down into this tail than is necessary. So I probably should not be reporting back this as an answer. Just keep in mind, the full-blown Bayesian answer is the posterior. But if you just go back to your scientists or your engineers or your advisors and say, here you go, here's a posterior distribution, do with it what you want. So you could even say, I'll let you sample from it, I'll let you do all kinds of things, I built an MCMC for you. So it's really efficient. Our job is to summarize answers for people. And so this is obviously not the greatest answer in the world. So what we might want is the shortest interval. And this is how you get it. So conceptually speaking, this is how I compute them in high dimensional space as well. What I usually do, if I had a bunch of MCMC samples, let's just say samples from the distribution. I can write down what the likelihood looks like, I can write down my prior, but this is a function. So I can't just look at the function and go, oh, I know where everything is. What you would have to do is integrate over different mass parts of the space and figure out how much mass is in the space. Instead, I can sample from that distribution, and by using the frequency of the samples, I can estimate that density. That's what sampling is. So what I usually do is I build some sort of a density smoother over it. Hard to do in high dimensional spaces. Then I discretize it all. I really do it in some sort of discrete manner. And then I add up how much mass is on this grid. And I'll do an example of this for you later. So where I wrote some code in high dimensional space to do exactly this. And then what I'll do is I'll add up the points on the lattice until it hits 95%. So, and I'll do it in the shortest possible way. How do I do that? Here's the idea. And there are packages, nowadays, you don't have to write your own stuff. Nowadays, the stuff is built in. So I think BOA and COA have this in R. So it's supposed to be the same picture right here. So what you do to get your highest posterior density or your shortest interval or set is you start at the very top of this distribution. So you take a line, you start there, and you look at how much area is under the line. Since I started at the very top of all of this, it's 100%. So probability 1 lives under the line. Then I just start dropping down the line. Computationally, this is what I do. Is I start lowering a hyperplane through everything, and I start adding up values and figuring out where it is. Then I actually have to redraw the contours around it. That's a hard enough problem in itself. So it turns out that's a solved problem as well. I found that out when I was writing this thing and spending like 2 days trying to draw contours around boundary points and going up. This is a problem. Computer scientists have solved this in the most efficient way possible. Let me go grab their code. So this is easy to think about because the sets are just straight lines. You can always do this in 1D, but in high D, you get the point, it's harder. So I'm going to add together all of the area under this line right here. So I'm going to get it all. This was defined by these boundaries right here. And what I might add up just under this wedge right here is maybe this is just like 70%. So maybe that's 70%. Keep in mind, you would have everything normalized. So that would be 0.7. Then you just lower it down until you hit 95. What you probably do is go over 95 and then back up a little bit. So do the bisector thing. So keep lowering until you add up more mass. So this one got a little bit more and it extended this part just a little bit out, a little bit more. So this number just went up when I added all this stuff up, and this went up to like 72%. So it's always going to be adding as we drop down. So I'll drop down a little bit more. This is the hard part to do computationally in high dimensional space, distinguish that from that and all the dead area in the middle. Again, software is already developed for you. So I'd add up all of this, and I would keep dropping this down until it hit 95%. So let's say I got here, boom, add that together, and at some point, you're going to get all the 95% area. Then after a while, boom, lo and behold, 95%. In reality, you have to come up with your margin of error of what you're willing to tolerate in everything. So when you discretize everything and you do it on the grid, you're going to have to make this grid that is, really refined. And in high dimensional spaces, that's really hard to do. And so what people will do is they'll be adaptive, and where there's more wiggles in the space, they'll make the grid more refined in that part of the space. So they'll look at the second derivative of the function or something like that. So full-blown PhDs, research papers, thousands of them have been written on stuff just like that. So we don't always have to do all the work. Instead, we can just think about conceptually what we're going to get back. I think this would be a much better description of what the highest, or what the interval should be, my belief statement. So what I would report back is L1, R1, L2, R2. So the set would be this. Union R1, oops, L1 to R1, union L2 to R2. And I would like that, because it would tell me right away, this is a bimodal problem. And if I were really interested in the problem at hand, that would tell me all kinds of cool things. Oh, there's like a mixed population in here, and there's two different behaviors, depending on where we're at. I also probably wouldn't be inclined to report back the map right here, but I would want to report back the local maps. So, to characterize the problem. That's all within our human understanding. There's no theory on this per se. It's just, what do you think your best characterization of the posterior distribution is? So, in a lot of cases, I just use the equal tail intervals. And that's what I asked you to do on your first homework set when you were doing the simulation with the betas, is just chop off the 2.5% tails. You could improve your simulation a little bit, for small n especially, because those distributions are skewed. So you probably want the interval to convey that to you. So depending on the skewness of the distribution. As n gets big in that example, that beta distribution starts to look more and more normal, looks more and more symmetric. And so then it doesn't matter. So for big N, you probably don't have much of an opportunity to improve the results for the Bayesian. But if you want them to improve a little bit, you might use the HBD instead. So it's usually just kind of a computational bear to work with, and people will just chop off the 2.5% tails. If the problem is multimodal, please go through the effort. I think what I'd like to do is spend Wednesday and just talk about some other distributions for a while. Make sure we've got a handle on what we're doing, and then move into MCMC. So probably should touch a Poisson distribution. Probably should talk about an exponential distribution. I know Josiah wants to talk about the uniform distribution. So the Bernoulli example I just gave you is one, because it's got this uniform sort of nature, and it's a uniform distribution that just has 2 points. But I don't think that's the example you want. You probably want one where the boundary is defined by the parameter, not the location. So it's going to work as a scale parameter. So probably need to write that problem down. Are there any other distributions that are super meaningful to you guys? Everybody know what a Poisson is already? Everybody knows how it relates to a gamma? Everybody knows how that relates to an exponential? Getting a lot of confirmation bias. Anyway, let's come back next time, just write down some other distributions, see if we can kind of see what the posterior predicteds might look like. We won't go through all the gory details. And then we'll jump into MCMC. And if you want to know more about those distributions, we could do those in review, or else you guys could band together and protest, and I can do it all in class with the recording. You guys will let me know. Thanks, you guys. That's it for right now. Welcome back. We'll do another 3-day weekend, not this week. We've got all the days of class, Wednesday, Friday. The next week, we're taking Friday off. I'll remind you again about that. Homework is due this Friday. I'll take them. Let's go. Lunch.